Back on shipping and receiving. I like this slide, just in fact, and I always like mentioning it because things happen. Oops, or FedEx or whatever you use, different freights, DHL or everybody. Things happen that are just you buy expensive equipment, right? It is so easy to spend a little bit of money and get a case, get a high density foam, and cut everything out. In this situation, load cells here, meters here, laptops here. They're using a Hattie system with the software. Super easy. Box it up, send it back to the company. Company ships it back to you. Chances of a safe return are highly probable. They're not 100% because people lose things, they break, they other things. Then there's the good. Really good is double boxing. This is more if you have a shipping, if you're going to do this, it's fine. If you're going to pay somebody to double box everything, over time, having custom cases is going to save you money and time. So I think it's a poor business decision. If it's your only decision that you have to do, I highly recommend it until you can get the custom case with the high density foam. The bad, maybe some people are on here, attendee list where you've invested, somebody sold you these systems where you're like, I just throw my instrument in and I have this blow foam that I can fill everything up. And every now and then we get this, and someone new comes in to, new eyes always appreciate points of view, but they say, hey, do you think we should switch to blow foam? And they say no. The reason, and I don't know what it's called, I'm just calling it blow foam. Heavy load cell and cable in this foam that's not a high density, it's heavy load cell always wins. And a lot of times we're calling customers to say, hey, your cable's severed, we can repair it. Depending on what the system is, it may not be an as received calibration, and that gets into learning a little bit of back and forth to see if we can still do the as received calibration. How bad is that cable severed? Is it just severed in one location? Or are we taking out like 6 inches, 10 inches of cable, all this other stuff? And then there's just the ugly. Someone just threw something on a skid and said, here, go deliver it. We've had that happen just as well. So yeah, just think about, oh, okay. Yeah, I'll answer that. We're going through load cells, and there's some good questions in the chat from Anthony and Elliot. So I'll go load cells. I have your questions, and I'll answer them as we discuss this. So types of load cells. This is not all encompassing of all the types of load cells that are available. It's pretty much what I consider the most common ones. You may have seen like piezoelectric and some other ones and say, hey, why aren't you covering that? Because we don't see a heck of a lot of those. So we have column load cells. Sometimes called single column or high stress load cells, multi-column load cells, S-beam or S-type. They look like an S, button or pancake, and shear web. This is what I'd say we see the majority of. Yes, we see piezoelectric. Yes, we see some other ones. We see well gauges, all types of other stuff that I haven't talked about. But these are the ones we start looking at. If I'm going to buy a load cell, what do I want to buy? Column load cell, fairly inexpensive and easy to make. Spring element is intended for axial loading and typically has a minimum of 4 strain gauges, 2 in longitudinal direction and 2 oriented transversely to sense the poisson. My French is bad. It's been 30 some years since I've had it. Strain. So yeah, most manufacturers are going to put 4 gauges in here. Some are going to be the exception. They're going to put 8 gauges, and 8's going to help. You're going to balance with, if you use 8, we would highly recommend 8. You're going to get better results overall. And it's not that expensive to go to 8, from 4 to 8. You already have the element and everything else in it. It's pretty easy to cut these. The material the material selections can be a little bit difficult depending on what material you go with. We made one time at a Viscount 40, I think it was Viscount 44 material. That was super interesting for us to do. We got really great performance. We also put 16 gauges on it. And you can do 32 gauges, you do whatever. In any case, easy to make. There's advantages of these is not uncommon. You want a big load cell, big heavy load cell, not uncommon to have it weigh less than like 100 pounds. And for those that are looking at NIST SP811, or not, yeah, 811, I'm going to call myself out here. This is not a unit LBS. This should have been LB. I'll fix it later, but I was looking at that yesterday and I didn't pick that up. So disadvantages, column load cells, reputation for inherent nonlinearity. Deviation from linear behavior is commonly ascribed due to the change in cross-sectional area, which occurs deformation under load. This basically means, look, since it's cheap to make, we're going to gauge it. There are some fallbacks with this, and a lot of the fallbacks have to do with sensitivity to off-center loading, which can be high, and hardness of the loading pad can change the output. And I just put a random number here. The number's high. You expect something, and I'll show some examples of this, but you expect something to be much better than what it is, and you should really have top and bottom pads with it. And larger creep characteristics. Remember when we said creep is underload or creep recovery? Right here, we're measuring creep recovery, which is a zero return. So of these two load cells, both are non-Morehouse load cells, both are single column load cells. And we applied the force, held the force, took the force off, and then we said at 30 seconds, we have a zero recovery. One cell is much better than the other. I mean, the one is at 0.0, or yeah, one is at 0.025, and the other one is at 0.0083. I would certainly want the cell on the right compared to the cell on the left, but that doesn't tell all. So multi-column load cells. In this type of design, the load cell is carried by 4 or more small columns. Guess what? It's getting more expensive. Does that mean it's better? Yeah, kind of. Each with its own complex of strain gauges. So right now, we're getting at, oh, look at this. If each of these have 4 strain gauges, 2 or more, likely 4 or more, already I have 16 strain gauges. And then these are all connected in a series of the appropriate bridge arms. Oh man, what's that gonna do? Well, it's gonna do a number of things. For the engineer that's designing it, it's gonna allow these cells to be more compact than the high stress load cells. It's also gonna allow for improved discrimination against the effect of off-axis load components because of the fact that we have the four different bridges. And they typically have less creep and better zero returns. Same type, same test here. And remember those other ones, that one on the left was 0.025. Now we're at 0.003. That's 3 parts per million. And in many cases, a properly designed shear web spring element can offer greater output, better linearity, lower hysteresis, and faster response. So these can also be small. This is a 600,000 pound mini load cell that we painstakingly built. And I say painstakingly because there were lots of iterations to get it right, get the gauging right, get everything else right on it. And it matters. And it matters big time on where you put the gauges, how you put them in, the technique, all this other stuff. So we got this cell right where it's a cell that's good to 0.01% of full scale. It's 600,000 pounds. And yes, the downside, and it weighs less than 25 pounds. For 600,000. And the big downside is it's much more expensive than a single column. So if you're looking for something for a technician to just be able to carry lighter shipping weight, put in a machine, take out of it, all of that, frequently transporting, ergonomic issues, probably worth the extra money. You're getting better creep characteristics, creep recoveries better. You're getting improved discrimination against off-center loading. You're spending more up front. Is it overkill depending on your application? Maybe. And that's why I'm going over all of this. So you can decide. I mean, the cost factor of it is like 2 to 3 times that of a single column cell. So if my measurement didn't need to be that, if then result is my measurement doesn't need to be that great, if I'm not switching machines, if I don't need that much of a loading range, if I'm not doing E4 cals where I can drive this load cell down to 30,000 pounds easily, I could have a loading range from 30,000 to 600,000 in accordance with E74 Class A, versus single column that's maybe 60,000 to, so what's that difference worth? There's a lot of considerations in here for the cost. Multi-column, Revere made and continues to make great load cells. We had this cell come in with a non-flat base, and I just did some repeatability test on it in rotation. Basically, the non-flat base came in and rotated it around, took the difference, kind of like we did that non-repeatability number, just took the difference in rotation with a non-flat base, and then actually took this base off and ground this surface, redid this exact same test, the exact same positions, and the numbers got, almost 4 times better. So little things like wear on pads, wear on adapters, if you're not parallel loading surfaces, they can make bigger differences in your data. One time on one of our dead weight machines, the screw was loose and the data was like 5 times worse in rotation because the things were flexing that shouldn't have been flexing. So that's why we have measurement assurance programs and all of that stuff, because we're not asking everybody to go, check tighten screws on every screw and everything else. But there's lots of good stuff from this. And the other piece of this is bottom plates. A flat bottom plate may be needed to improve performance, but more than improving performance, it typically will protect customer equipment. And there's a 60K rod end style. This is a tension compression load cell. It's sold as part of the typical concrete kit for field use. And there is the full concrete kit with adapters. It's full kit. The range that people get is like 200 pounds to 600,000 pounds of force compression, and then they get 200 to 60,000 in tension with that. But why do we have that? I mean, if you have that bottom plate that's a little bit softer than the load cell, the chance of this happening is significantly reduced. And you can see this is a good method to see how well your technicians can center something on a beam. Though the funny story with this is my friend had attended an NCLI workshop where I did a very similar class. And then like 2 weeks later, he's texting me. He's like, guess what? I had your class and I know better. And our company still did this. And he was laughing about it. I said, can I use this? And he said, absolutely. So yeah, this is why you want bottom adapters. You don't want to go out and be marking customers' machines, because you're going to have to, with that non-ground adapter, your errors here, if you start marking and do not have parallel or flat surfaces, are going to be a lot higher as well. Another example of adapters not being used, this is a Cal machine. You would have thought the customer learned a lesson in like 2017. I think we resurfaced the plates, and then 3 years later they were still doing it, and we gave them notes and said, use pads in between here so you don't do this, because it's really expensive to tear down a machine and regrind it, and to regrind a pad or a load or a throwaway adapter, I don't call them throwaway, but if to regrind those, like $40 compared to, several thousand. So for those beginners, that 40-some% of beginners, use pads between stuff, because if you start marking equipment in the lab, it is a major pain to fix it. So S-type cells, all kinds of capacities, 4 gauges typically placed inside the beam. Advantages galore. Cost is usually very cheap. You can probably go to Amazon right now if you want to do the test and say, hey, give me a 100-pound S-beam, and you probably get one for $30 or less. Linearity will be enhanced by minimizing the ratio of deflection at rated load to the length of the sensing beam. Change the shape element. They're ideal for measuring small forces under 50 pounds when physical weights cannot be used. I don't even know if that's true. If they're used in tension, they can be pretty good. I'm not a huge fan, and I'll show you why. Disadvantages. This is why I'm not a huge fan. Is they're very sensitive to off-axis loading. Compression output will be different if the cell is loaded through the threads versus flat against the base. And I have a slide later in the error part, or not. I have a slide later showing that. And then you just look at it. Does anything look different? I mean, you're looking at two pictures here. Just look at them. Anything look that different? How about now? I had to draw a green line through them. But if you do the math on this, it just is slightly misaligned in the machine. And the output varied significantly. This is one of the worst S-beams I've seen. This is probably equivalent to one that you may get on Amazon. You may get good luck with the $30 one. Though we calibrate this and then somebody just slightly misaligns it and the difference in output is 0.75%. And when I say we calibrate it, so it goes out the door. On the left is an uncertainty analysis. There's these bars, how much uncertainty is contributing to the, how much each individual contributor is contributing to the overall uncertainty. You got small, and there's a little bit on stability. The S-beam LLF there and repeatability. So output in millivolts aligned in the machine, expanded uncertainties was about 9.95, right? It's aligned. This column over here, this misalignment error. If we misalign that and redo an uncertainty analysis and say, look, I had this 0.752% of error, it becomes dominant. And what ends up happening is we send something out the door to a customer and they're sitting there thinking like, hey, one of my larger components of uncertainty is this ASTM LLF, which is basically how well the cell reproduces, what is the reproducibility of the cell when I vary conditions, like rotate it around, test the machine for, level, all this other stuff that can through the compensation section that can differ the output. And then I misalign it just a little bit. I take out an alignment plug, misalign it just a little bit, and I get a huge error. So really, if you think about it, if the technician perfectly aligns, or not perfectly, really well aligns the cell, aligns it well, they should have about a 10-pound maybe their uncertainty expected about 10 pounds. If they just are in the field and slightly misalign it, what they think they're measuring to within 10 pounds, they probably don't know to within 85, 90, 100 pounds. So it's pretty significant, and the error sources here are significant. Here, I had my son take some of these pictures. One of my sons take these pictures. So the concept here is basically that I have an S-beam load cell, and I'm varying these loading conditions where things are threaded at the top and bottom, and I'm either threading it, I'm loading something where I thread it against it, I back off the threads, or I load them flat against the threads, or thread one end, load flat against the other. So basically variable loading conditionings on the S-beam load cell and differences. So instrument reading thread loading loose both ends. That means nothing's tight against. Everything's backed off. And we're loading through the top and bottom threads. Instrument thread loading both ends, we've screwed the threads down. Loaded flat top and base, and then flat on flat. Thread loaded top, flat on base. This is probably the most common that I see people do is you load it flat and then you have thread loading on the top and then flat on flat. And what's interesting here is you have 4 different loading conditions. A customer sends you this load cell and you have no idea most of the time how they are loading it. And your chance of getting it right might be 1 in 4. Now, chances are they're probably either using um, this method or this method, which still only gives you a 50% chance of getting it right. Maybe they're using this other method, so now you have a 33%. Often find that this method over here is most customers are not using that. So we have a 33% chance of getting this right, but the maximum difference, depending on what method I use, was 0.369 to 0.298. And even the smallest difference was 0.29 or 0.3. So if somebody wants to calibrate and use this device to calibrate a customer's device that's where they want their accuracy specification is 0.1% a full scale, how much confidence are you going to have in that lab, right? When you have a 1 in 3 chance of possibly getting it right and a maximum difference that's roughly 3.7 times what they might be expected to calibrate. So that's the problem with S-beams. There are some solutions that make it better, and using alignment plugs, we can machine holes here in our machine holes that is darn near as close to center as we could possibly get without, using a CMM, a coordinate measure machine and whatnot, and give a better chance of at least aligning that S-beam. It still doesn't solve the need to ask the customer how you are using it, in which case you probably know you're dealing with purchasing or somebody else, and, oh, we just load that this way, and they don't really tell you. So just be forewarned. Button load cells, if you've ever calibrated them, you probably scratch your head. They're absolutely horrible. The specification sheets say they're so great, and yet 0.1% of misalignment can produce a large cosine error. If you feed it with 5 volts versus 10 volts, 10 volts might make it hotter and the output will change significantly. If you decide to warm it up and take a half an hour lunch break, then like warm. So it's, what is it now? 11:47. If I decided to plug it in right now and I went to lunch and we all came back at 1 o'clock, I might get a different output than if I just warmed it up for 20 minutes. They just are small load cells and they have lots and lots of problems, and errors anywhere from 1 to 10% of the rated output. Cells on the right, they're made by HBM if you need them. The smaller one, they're called burster cells. Highly recommend them if you need small cells. Of course, they're super expensive, but that's the price you pay to get something that actually works in that small capacity. And you get stuff like this. I call this the cheeseburger, which means basically you have your bottom plate, you have some top adapter, and then there you have the meat, and the meat is actually the button load cell. If we use this type of adapter, which I would imagine 99% of the labs are using, and just squeezing on these cells and reporting the data, we get really bad results. And this is where we see this. Look, if I just vary the loading conditions, just rotate the cell around, I get a deviation. I keep it centered. I just basically randomizing and moving it, which means I take this when I often say randomizing, which I mean I maybe put the connector facing me this way, then I move the connector to facing that way, and then that way. So I have 0, 120, 240 degrees. So I do that. I get those numbers, and then I'm reminded of my good friend mentor Dilip Shaw that says you can have your head in an oven, feet in ice, and on average you feel fine. Again, average 2008.66. We use better adapters on the right average 2008. But what do better adapters show us? Well, better adapters say, hey, I have a better chance of repeating these results with these more precision adapters, to which case the actual error when I did my 0, 120, and 240 rotation improved by a magnitude of 525%. Now, this is not the end all be all. I would love to sell you these adapters if you do not have them. Your technicians will love you for buying these adapters for them, or if you're a technician and you want better results for customers, the adapters will absolutely help. They are not the end all be all, though. These cells still have problems. They just make it a lot easier to calibrate the devices. And when we start looking at adapters, guess what? Of course, every manufacturer designs different buttons, which means you need different top adapters. And then this bottom plate, yep, uh, go find 5,000-pound button load cells from several manufacturers and washer load cells and whatnot, and you'll find a whole slew of different sizes. And we did not standardize anything, thus we need multiple adapters to accomplish the calibration, and multiple adapters add to the price. Again, not against it. I encourage everybody to get adapters because it's the fact that we can align things and we get things so much better. It's just they are not the end all be all. But people need to calibrate those load cells. Shear web cells, my favorite load cell. I call this an integral adapter. Some other people might say it's not integral, it can be taken out, whatever. It's a threaded adapter that's locked into place. When this remains locked into place, these are probably one of, if not the best load cell as far as calibrating consistently. We see numbers. I've done a paper on end of period reliability. I've done papers on all kinds of stuff with good meters. If you want a very, very good load cell with the right meter, this load cell stacks up. If you want to pay a lot more money, there are better load cells. But you start talking about how good do I need to be? If I want 50 parts per million, this is my load cell. If I want a meter that reads 6 decimal places instead of 5, now I'm going to have to spend 70 grand instead of like 10 grand. So, and I mean 10 grand for the load cell, the meter, the cal, all of that. It's actually less than that, but versus like 70 to 80 grand. So depending what you want to chase, the cost gets exponentially higher after what I consider this, which is a very, very good load cell. If you want to chase like ridiculously low numbers, like 20 parts per million or lower. So recommended choice for most force applications. The problem with these cells is the weight. After 100 pounds, and people complain a lot on 100 pounds, it's 57 pounds. So if you're mounting it in a Morehouse UCM or other machine, you can set it and forget it. If you have to change it out, not the end of the world. If you're a field tech, you don't want to carry a 57-pound cell around. You just doesn't. Field techs will complain about a 20-pound cell or a 10-pound cell sometimes. So, and I get it. You have to schlep all that stuff around and do all the other stuff. So I completely get it. But yeah, if you want the best, this is the best cell. They get super heavy, super quickly. So we look at this. We look at creep zero return, creep recovery test. Not as good as the multi-column cell, though this cell will give you much better performance overall than the multi-column. It will beat it by a factor of 2 or 3. The creep zero is not as good. So looking at this type of load cell, the same shear web. This one, though, deliberately misaligned this load cell. This is horrible. Right? I would hope a technician would never do this. Of course, I'm the one that did it, and I did it for these purposes because I wanted to see, we have specifications, we've tested everything. I wanted to throw it in the machine and say, I want to put it in a dead weight machine and pretend I'm a sloppy technician, just be stupid with it, like whatever. And what ends up happening, if we look at the S-beam slightly misaligned, that goes out the door with 10 pounds. as I said, about 9.95, and in actuality, when you misalign it, you're making a measurement with an 86. So this load cell goes out the door at about 0.417 pounds of force, and if you misalign it, you're adding like 0.11. Very, very low error that's being added to this cell overall. So what we get, and what I don't like at all about these load cells, is the way they are designed and the way they can compensate for that off-center loading and some side moments and everything else are such that they need to be, the design characteristics of them are such that this adapter needs to be, this integral adapter, what I call integral, or the threaded adapter, needs to be locked in place. As soon as you take this adapter out, and what do a lot of people do? And I know what they do. They go to Interface, they go to Tovi, they go somewhere else, not us, because but some people ask us to take these out and we try to fight them. Um, they buy these cells. They don't buy the integral adapter because they're cheaper. Like it's $100 cheaper, right? Depending on the type of cell, it could be more than that. And they don't buy it. And then when they don't buy it, you have this thread depth problem, which means basically, hey, if I engage this load cell the way it's designed at different thread depths, I'm going to get a different output. So this picture is showing that if I broke this thread loose and I didn't engage the full thread engagements, like 1.1 inches, and I only engaged it an inch, or 0.9 inches, or 0.85. So I only engaged at 0.85 inches out of what I could engage it with 1.1 inches. The difference in output is going to vary from 0.184 to 0.138%. Just this test. You could do another test and it could be 1.2. You could do another test where it could be 0.2. You could do another test and only load it 5/8 18, 10 thread turns to get 5/8 engagement, and it could be a 0.5% difference, right? So not a very good load cell if you're going to vary the thread depth. A fantastic load cell if you're going to lock an adapter into place. And you get numbers that are super low on your calibration, and as soon as you break this adapter out, you void that cal. I don't know what your output's going to be if you thread it 5/8 of an inch versus 1.1. Each cell's different. It's not been tested that way. A different design load cell that looks really familiar to the shear web load cells, the biggest difference on these cells, and it's hard to explain, is that this piece, all of this right here, this is a solid core piece. It's machined as a solid piece. It's made out of stainless steel. We subcontract these load cells overseas to be made because of the fact of all the material and everything else. So they cost less than the traditional shear web cells. We call them our budget cells. Are they as good as the shear webs? No. Are they pretty darn good? Yes. If you're looking for, an S-beam is like too cheap, you're not going to get what you want with that. A single column, all this other stuff. This is that happy medium load cell. Where it's got a lot of the same characteristics as the shear web cell, yet it's made overseas, and we keep them in stock, calibrated. They're good. They're good cells. I can't say anything more. Same test with this cell, because it has a different design, and this is a better picture to show you. See this piece right here? All this piece comes out. In this load cell, this is a permanent piece, and only this top's coming out. And there's more, I say there's more meat there in the design, and I can get nerdy about that, but this cell, if you do the same test with it and you back it off, less sensitive because there's a lot more mass in the center. Now, is it as good as compensating for off axis and all that stuff? No, it's not. So in that regard, you have to say, all right, what do I want, right? If I don't have enough money, or I want to save some money here, it's perfectly fine for E4. It's perfectly fine for most applications. I just wanted to let you know, though the other piece is just slightly different design cell will give you trade-offs. If I wanted to use this cell in small spaces and remove the top adapter, I certainly would recommend the cell on the right versus the cell on the left because of these errors are just too high on the one on the left if I want to take this adapter out. Alignment, when we start talking force for the beginners and the advanced, for everybody, but the beginners probably haven't done enough testing to know this just yet, that I want to align everything. If you haven't told, that S-beam was a good example, 0.752% error, absolutely atrocious when I misalign it, right? So if I keep that line of force along that main loading axis, and I start talking about things like eccentric forces, the actual load line, the difference between the actual load line and the main loading axis, it would be an eccentric force. And keeping the force free from it is the key to calibration. And how do I do that as a technician? Like, I have to use the right adapters at some point. And we do a lot of business just selling those right adapters. And it makes the technician's life so much easier if you have those, if you can get things aligned in the machine. Now I'm not fighting. I'm not making those customer calls that say like, oh, well, I needed something good from 10% to 100%, and we're giving them 20% to 100% because we don't have good alignment when we do their calibration. We try to model all of our adapters in line with ISO 376 2011. And that standard, I haven't bought it in a while because it hasn't been updated and I'm part of the committee, so I know what's coming out. I believe that standard is 100 some dollars, 120, 130. The annex has how you make all of these adapters in it. This is, this is one of our drawings, but it has everything in it. You can buy that if you wanted to have a go at making your own adapters or doing things. I recommend following it. And I recommend having a copy of the standard because I think the price to support that committee, that standard, I think it's well worth whatever they're charging, $120 to $200 to get that annex and have all of that information if you want to have a go at making your own adapters. Load fitting should be designed A4 in such where the line of force is not, application is not distorted. Tensile force should be fitted with 2 ball nuts, 2 ball cups, and if necessary, 2 intermediate rings, while compressive force should be fitted with 1 or 2 compression pads. Okay, those are good rules to live by, and that's why they're here. Like I said, that's copyright ISO 376. Buy the standard if you want to buy it. So I'm going to give you some tips here. Making adapters seem super freaking easy, right? And this is one that this came off of the machine, came off of the lathe, and someone didn't do the finishing on it, and they blackened it, and we did some testing with it, and then we said, oh, this testing absolutely sucks in our cow machine. Really bad. You can tell there's coarseness to it, and we said, okay, let's see what happens if we go back and finish it. We weren't so sure. I was pretty sure the finish on it was garbage. It should, if you have stuff that looks like that, it should be smoothed out. Stuff should never leave like that. Luckily, this was internal. So we smoothed it off. Had a nice council session with the machinist, and now you learned your lesson and you don't do it again. And the results were pretty dramatic. And when I say dramatic, just rotating it around 0, 120, 180, 0, 120, 180. Typically we do 240, but we were doing some different test here. But the point is comparing like measurements. If you get into comparisons, and this is where I detour off track sometimes and stuff, but if you start getting into comparisons, make sure you do like comparisons to try to determine what the source of error is. If you have too many variables, I don't like my numbers, so I'm going to swap this out, and now you've changed 3 or 4 things. It's different, and now it's good. what one of those three or four did you change that made the biggest difference, or did they all make a difference? So it's good to know these things. This one, the only thing was varied was the flatness or the smoothness of this adapter, and we went from 0.122% in rotation to 30 parts per million, or 0.003%. Pretty dramatic difference. Though this slide is here as a key, and it's also here as to show you that making adapters, even though it seems simple, people forget the little things like just surface finish of them, and that can have a huge impact, and it can cost you a lot of money, because imagine if you're doing cows and you're rejecting a lot of good product, a lot of good instruments that are actually good, and you're calling them bad. That's not a situation you want to be in. And if you've done that for a year or two, and right now you're just having this course and saying, I wonder what my adapters look like, and you go find that they're all rough, go finish them off and do your evals. So tension adapters, what do we see more of? Hey, I went to A's True Value, I went to blah, 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 I bought this. We see more of this happening. If any of your tension adapters look like this, there's a problem, right? If you played pool, you roll your pool cue and it wobbles, you go grab another pool cue at the bar, or you buy yourself another pool cue. The same thing with they shouldn't wobble. Right, dramatically. Of course, everything wobbles, but they should be straight. Even straight rods can introduce issues. They can distort the line of force in machines. Any machine misalignment can affect reproducibility of some load cells. Just depends. You started going into the different load cells and how they're designed. We could spend 2 days just on load cell design. We could spend weeks on it. Um, but yeah, system there, basically 2-ball nuts, 2-ball cups, spiracles at the top, put it in the cow machine. We got into this big thing with quick change adapters, which basically some people buy eye rods, ball socket joints, all this other stuff. These adapters, you buy a pair of these adapters, and then what's quick change is these, right? So a different load cell comes in, all of a sudden you're dealing with a load cell that's 5/8 18, and somebody sends you an 1.25 inch load cell or something like that. You just switch out you just use these different adapters, and you can make these adapters. You buy the tension members. I think we're really good at making both, but you could buy the tension adapters, and if you had a machine shop, it'd be super easy to cut your own adapters on these other sides if you needed them, or you can just get them from us. It all depends on what you want to do. So compressive force pads, ISO basically recommends should be fitted with 1 or 2 compression pads. Their design is right here from that ISO annex. And then here is one that we made very similar to their design over here. So we have them. Here's where it is modeled. This is what they recommend. The top, we call it a CI adapter. I do like these adapters a lot. I like them in cow machines to avoid ball-on-ball loading, because you can have some distortion for that. So your unit under test area, these compression pads, and guess what? They're flat. So those that are new, flat, guess what? You don't mark the top and you use a loading surface, you're not marking the top of the machine like if you're trying to press a ball or other adapters into it. So really good practice. We've had a lot of success with those.